In this video on systems of equations, we're going to be looking at our first non-unique solution system. In this video, we'll particularly look at infinite solution systems, just like in the diagram here. Now, we get infinitely many solutions when we have three planes that all meet along a line rather than at a point, like this. And because there are infinitely many points along a line, that means that there are infinitely many that lie on all three planes and also solve our problem. This contextual example is almost exactly the same from our previous video, except I've changed a couple of the numbers. And by doing that, I've actually changed the type of system that we're looking at, because the numbers in our problem here, which are also numbers in our equation, determine the type of system that we have. So let's put them into our solver. Foo pack A will be an equation in the top row, and we're just putting in our coefficients now, and then the constant term. Let's go ahead and solve it. So we get a solution, although the solution does look a little bit weird in this case, for example, having negative $3 per gram for protein and fats are free. However, more importantly, we come up with this error message over here, which says that the system has infinitely many or no solutions. Now, this didn't come up before when we had a unique solution system. So this is when we're dealing with a non-unique solution system, and we need to figure out whether it's infinitely many or no solutions. Well, this suggests that we have infinitely many because the solver actually gives us one of them, so there are probably more. Let's look at this geometrically to see what's happening. When I graph all three equations as planes in three-dimensional space, you can see that they all meet along a line. And in fact, those 3 points there that I've indicated as A, B, and C are just 3 example points along that line. There are infinitely many of them. The first point, point A, is the same as the one that the solver gave us. However, points B and C are other examples of points that also solve this problem. For example, with point B, the price for protein is negative $2 per gram, carbohydrates is $2 per gram, and fats is $1 per gram. That also meets the requirements of food packs A, B, and C from before, and so does point C and every other point along that line. So why does this happen? Why did this particular combination of food packs A, B, and C give us infinitely many solutions rather than a unique solution like before? Well, the first thing to understand is that this is a consistent solution system. Just like in our previous video with a unique solution, that was also consistent. Because consistent just means that if we have one solution for one plane, it is also a solution for all the other planes or equations too. But more importantly, this is also called a dependent system, whereas the unique one was called an independent system. We call it dependent because if you look at the equations, you might notice something. Here's our equations from before. I'm going to put the coefficients in here just to make it a bit more clear. Do you see it? The coefficients in the first two equations add up to make the coefficients in the third, and the constant term in the first two equations add up to make the constant term in the third. So the third is just a combination of the first two. So if we look at food packs A, B, and C, C is just A and B together. It's nothing new. It's a totally useless piece of information that we could have figured out ourselves. So what you want to look for to determine a solution system like this is that two equations add to make the third exactly. So what that means is that this third equation here is actually redundant. It's useless. So why does it give us infinitely many solutions? Well, think about two planes meeting in space rather than three, because that third doesn't actually do anything now. We've got two planes meeting in space. Unless those planes are parallel, they must meet along a line. So no matter how we position them, we must get infinitely many solutions. And that's it. Thanks for watching.